Yes, yeah, welcome back. Today we are going to learn about the Truss equation. So maybe the chapter 3 of our lecture material of the FEM lecture by Logan textbook. Today learning object is to derive the stiffness matrix for the bar or truss element. So we are going to use direct stiffness method first, and also I think we can also use another method, for example, potential energy approach method and Galerkin residual method. I think that, and also this truss element can be expressed in the one-dimensional spaces first, and then we are going to changing or rotate this truss element into two-dimensional spaces. So that I think that this is the first introduction of the how to changing the vector direction in the two-dimensional spaces, or you can I think you guys very smart, you can also freely changing the three-dimensional spaces after the learning the transformation of the vector. So I think that we can compare our analytical solution with the commercial software result. So, and then I think I'm going to prepare some lecture material for the developed of the code for the FEM truss element. So after the learning both theory and development of the code, and then we can compare our solution very systematically with commercial software. So today we are going to learn about the basic theory of the truss element, and then after and also please remember another method to derive this finite element equation, the Galerkin residual method. This is also another numerical method to obtain or derive the discretized equation for the FEM solution to the matrix form. So compared to the energy method, this Galerkin residual method use a finite difference equation itself very similar form. So first time it is harder to understanding the Galerkin residual method directly, but after when you understanding how to use it, you can easily discretize any partial difference equation. So I like those methods, so that I'm going to introduce to you guys. But I think that to solve the spring, truss bar, and beam element, direct stiffness method is enough. But for the derived plane stress and strain system, we need those kind of advanced technique. For example, potential energy approach method or Galerkin residual method. So please remember after learning those kind of methods. And also, we have another topics, symmetrics. Maybe those two things I'm going to prepare the next PPT lecture slide. So today we are going to learn about the first how to derive the truss element system. Those kind of analysis can be used for the designing on those kind of bridge construction. This bridge is a very famous application on the truss system. This iron bar, we can easily assume that they follow the truss behavior. So after the designing, setting those kind of structure using as a bar element, we can obtain some deformation of this solid structure, and then reaction force, and from here if you know that cross-section area, you can also derive the stress on the solid structure. So that after the calculating those kind of complex structure. I think that although you learn about solid mechanics, we cannot solve those kind of structure. It is because that to determine those kind of structure, we should know that reaction or boundary condition can be solved by mathematically. But when you learn about the numerical method, for example, finite element method, you don't need to worry about that. After the designing using the CAD software, or just put some the node element information, so by FEM method we can obtain some solution if the boundary condition or some other material property inserted into this system properly. So anyway, using the numerical computational method, we can designing those kind of structure. So I'm going to next time, if I have free time, I'm going to introduce more good application or example for the FEM simulation. First let's focus on the truss element first. This is some basics single element of the truss element. Also similarly, spring element, they have two nodal point in single element. Compared to the spring element, we should know that the length of the element and then cross-section area. And then like spring constant, we also have elastic modulus of the solid structure system. So that we should know that these three information for the designing the truss element. And then similarly, we have two nodal point. Each nodal point has a displacement and force variables. And then we have external forces. So this solid structure, truss element have a very simple assumption. We neglect the shear forces or bending moment, and in other way, we are going to neglect transverse displacement. What is the transverse displacement? This means that displacement over vertical direction. We are going to neglect the vertical direction or y direction displacement in the this solid structure. So we only handle the one-dimensional displacement. So this solid structure naturally follow the Hooke's law equation, so that this relationship looks like this, very linear relationship from the strain or stress or some displacement, some forces. So it's very simple cases. So anyway, here T is forces of on the truss system, and this forces is equal to the cross-section area multiplication of the stress. And stress is follow the Hooke's relationship, maybe can be expressed the Young's modulus and strain. We only handle the strain in the axis directions only, so we obtain those kind of a relationship. And then strain is defined by the ratio initial length and then increment the length of the solid structure, so that this increment is in this element we can easily determine the displacement of the U2 and the substitution of the U1. So the final relationship and look like this. And then similarly, so we can easily determine the force variable F2, so is equal to the T. And then however the F1 maybe have a different sign of the T, so that the force equilibrium looks like this. And then we have a two linear algebra equation. We can easily combine or transform to the matrix form. Here this equation equal to the Ku equal to F. In here, K is a local stiffness matrix of the truss element. Very similarly, spring element is look like this. spring element. Yeah, bar element, similarly, spring constant changing to the cross-section area Young's modulus over the length. So this is a truss or bar system. So yeah, this is a local stiffness matrices of the truss element system. So we can obtain the single local stiffness matrix equations. So after, if you have more element, so you must assemble this local stiffness matrix into the global stiffness matrices. So yeah, this is a very simple. We already know that how to assemble the local stiffness matrix to the global stiffness matrices. So so I skipped this detail. So yeah, I also introduced the second way to derive the stiffness matrix of the bar element, truss element. So yeah, let's begin to the solid mechanics lecture. So we have some solid structure, looks like this. Yeah, this bar, yeah, attached on the wall, and then we have external force T in here. Yeah, to check the force equilibrium, we need I selected the representative volume element, or yeah, so free body diagrams of the simple part. Yeah, in here, yes, there are some extraction force, surface forces in X position, and also this RVE has a finite, small increment length. So we also have some forces, extraction forces at position X plus and delta X. In this stage, yeah, we didn't neglect the body forces, so we included the body force. Yeah, maybe for example gravity. Yeah, we don't need it. Actually, we don't need it to the gravity force in this system. It is because that gravity force is very extremely low when you're designing very small size of the solid structure. However, when you're designing very large scale structure, for example bridge or some building construction, at this time you cannot neglect the gravity forces. So to design those kind of structure, huge, extremely huge size, so that at that time you should contain gravity force into the solid structure system. So anyway, yeah, to designing the truss element, we must know that cross-section area of the solid structure bar element, and then Young's modulus. Yeah. So anyway, this is a material information. Yeah, first we should check the force equilibrium in X direction. All summation of the force in X direction must be equal to 0. So that we have two traction forces at the X plus delta X and X position. They have two different sign. Yeah, this is a plus, this is a minus. Maybe this is a X, this is a X plus delta X. Yeah, in here we have a body force Bx. Maybe, yeah, we have a body forces, so that we must integrate the whole part, so that I use the tau values. This tau value ranges X to the X plus delta axis, so that after the summation body force, these three force term must become to 0. And also the above the equation, force is due to the stress, the transverse load must be can be expressed like this. If we have some internal resistance, I mean the stress, we should integrate the whole cross-section area. So yeah, this must be equal to T. So we can simply say that T is equal to the sigma stress and cross-section area, and then yeah, also yeah, stress and then cross-section area at that point. And also stress is a function of the X, so that you can you should check the carefully. So actually anyway, so this integration part using the mean value theorem, so you can simply reduce this integration part, looks like this, equation. So, and then we have a finite lengths, and then some average the body force can be expressed the inside value between the x and delta plus x. So, but in this stage we don't know exactly the details, but yeah, but we are going to use a very constant, simple constant value, so that yeah, in this stage don't worry about, yeah, just neglect it. So anyway, so after the dividing this whole equation by delta x, so that, and then after then we are going to this part infinite, we are selected very small, very finite size, infinitely small size of length, so that this equation looks like this. And then finally we obtained some different equation. Yeah, in this stage we have only single one unknown variable, so that this equation become ordinary difference equation. However, if you have, when you have two more variable, for example the two-dimensional spaces or three-dimensional spaces, at the time x and y, z, you can, yeah, this equation become partial difference equation, or yeah. So however, in this time we have only single, yeah, domain variable axis, so that we obtain the ordinary difference equation. And just remember that Tx can be expressed as sigma and cross-section areas. So after changing here, and then yeah, remember the cross-section area and stress, and Hooke's law is followed, stress is follow the Hooke's relationship, and then here strain, yeah, strain is a ratio the initial length and the increment length. However, we can easily say that this value is equal to the displacement of the derivative of the displacement. Yeah, this x is equal to the initial length, and increment is a displacement variable, so that finally we obtained in the previous slide, yeah, this t equal to the b equal to x. Yeah, t become the sigma and cross-section area, and then yeah, stress become the follow the Hooke's relationship. Finally we obtain the yeah, cross-section area and Young's modulus and derivative displacement, and then yeah, this part, and also derived by x. And again this, yeah, this is a final equation, yeah, actually governing equations, yeah, or equilibrium equation in solid structure. Yeah, governing is a general equation. For example, yeah, in the fluid dynamics, yeah, or other dynamics, they have a different governing equation. Yeah, in the solid mechanics, the governing equation is an equilibrium equation. Sometimes I'm say that what is the governing equation is just express the representative partial or ordinary difference equations. Just say that those kind of equation to me. So anyway, this is a equilibrium or governing equation in the solid mechanics. So that after the obtaining this value, before we continue the more details, so just remember that yeah, in the solid mechanics we normally check the many stress or some forces or reaction forces. However, in this equation, what is the unknown variable? Yeah, unknown variable is A is a cross-section area. We already know the Young's modulus is a material property. Yeah, body force. Yeah, basics. Yeah, physics of the some in the solid structure, inside solid structure. So we cannot control. We already know that. Yeah, but the remaining thing is U. Yeah, in the solid structure, so governing equation is equilibrium equation, and then main purpose this equation, we want to know that displacement of the solid structure, so that just remember that stress in the solid structure very important to determine the mechanical stability of the solid structure. However, all solid structure or forces derive or result of the displacement, so that the main key value or parameters variables is a displacement. Similarly, fluid dynamics, fluid, what is the key variable in this system? Maybe velocity or pressure. Dynamics, also displacement or velocity, or thermodynamics in temperature. In the solid mechanics, displacement. We have some, so that in those kind of field, these your governing equation is representative by those kind of main variables. So that just memorize those kind of things. So anyway, here this equation, second derivative equation of with respect to the x, so that the resultant of the u is can be expressed quadratic forms of the equation, so that we can easily obtain the solution by integrations. But to obtain the simple result, we assume that cross-section area and Young's modulus and body force is constant. Just assume that. And then after changing the Young's modulus and body forces look like this, and then you can integrate by simply move to this part side, and then integrate this part. This constant become a function of the x, and then we need some integration constant, first integration constant, and we have one more integration with respect to the x, so that integration once, so that this part becomes second quadratic form, and this integration constant become a function of the x, and then we obtained one more integration constant, C2. In here, to determine the exact u function of the x, so we need the two boundary condition. To determine the C1 and C2, we need some two more boundary condition. This is a very simple mathematics. So how can we determine the first boundary condition is this is u. Displacement x must be x, position x1 must be u1. Similarly, at x2, this displacement value must become u2, so that after adding the x1 must become u1, and u2 also can be matched when position x2, so that you can solve this. So we have two unknown variable, we have two equation, so we can obtain the C1 and C2 by numerical algebra, just linear algebra, so that to collect and C1 and C2 variable in the left hand side, and remaining thing put some the right hand side, and then combining the same things in here, and then using the matrix form, you can take inversion this value, so that after the taking inversion, multiply this inversion matrix into the right hand side, so that we obtain those kind of equation. And then to simplify, the x2 minus is x1 is a position of the at each nodal point. This nodal point has a length of the L, so that we can use those kind of things. And then after we in previous slide, displacement u as a function of the x, so that C1 and C2 we already obtained the result. To put the exact C1 C2 value, we changing this scalar form to the vector form, and we already C1 C2 in the previous slide, so that put the result in this part. And then here Yeah, so that's very complex form. However, our final goal is to describe the displacement u as function of the x, so that this and then well organized looks like this in here. Yeah, u1 and u2 can be expressed looks like this. At this part I multiplied this here and this here, maybe 1 by 2 and 2 by 2, that's become 1 by 2. Yeah, right, result. And then this part 1 by 2 by 1, and then yeah, 1 by 2 become a 1 by 1 scalar value. Yeah, this is a scalar value, and then combining this, yeah, b0 x square. Yeah, so the result and looks like this. Yeah, displacement is a function of the x and x. So we already expected the result maybe quadratic form. It is big, yeah. So however, when you neglected body force term, yeah, here, yeah, they containing x square, but here there are no x square term. Yeah, they must always become 0, so without the body force term. So that in the previous slide, that's why I mentioned that this become to blah 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 blah. So yeah, without those kind of term, we always obtain this become the 0. So yeah, if you want the force equilibrium, yeah, body force term always match, always express the second derivative, second quadrature form, and then stress or strain relationship expressed by a linear form of the x. So anyway, yeah, we obtain the exact displacement form. And here, yeah, please remember this red part. So, and anyway, so after the derived with respect to the x, we obtained those kind of result. And here, and then next important things is I want to check the force. Yeah, traction force T is expressed stress and cross-section area, but we use same cross-section area, so final form is looks like this. We already obtained the displacement derivative of u with respect to the x, so we already know that this part. So combining these two equations in here, we finally obtained here. Yeah, this traction force at x equal to x1 must be T x1 is similarly f1, but yeah, different sign. Yeah, sorry. And then yeah, position x2, yeah, force and traction force must be same signs. So that yeah, so after the inserting the x1, yeah, where is that? Yeah, x1, the result, yeah, this part always same, and then this part become the x1. We have a 2x1, x1 minus x2, and then if you put on x2, x2 minus x1, so we obtain those kind of result. Yeah, neglected this part. Yeah, we have a two linear algebra equations. We can changing the matrix form here. Linear algebra equation, same form f equal to ku, but in B side we have one more additional term is body force term. So in the previous derivative of the stiffness matrix of the bar element, we neglected the body force term. However, when you combining these two terms, or when you neglected this force term, you can obtain the same form of the local stiffness matrix of the truss element. So that similarly, yeah, this part, yeah, K part is a local stiffness matrix. Yeah, U is a displacement vector. Yeah, is F equal to the force vector. Yeah, this is a second way. However, yeah, just remember that, yeah, if you don't want neglected body force, yeah, actually body force is known values in our solid system, so that you should add this part to the fourth side, not left hand side. So yeah, I'm going to mention about those kind of thing more details. So anyway, so this is a second way to derive the stiffness matrix of the truss element. Similarly, you can also derive the beam or other solid structure systems. So just remember that. So anyway, those kind of method, we can obtain the local stiffness matrix of the truss system. However, after obtaining the local stiffness matrix, we should assemble this local stiffness matrix to the global stiffness matrices. So that after then, our final goal, we want to know that this nodal displacement. So that to obtain these variables, we should apply some boundary condition depending on your system. But without knowing those kind of boundary system, we cannot solve it. So boundary condition. What is the boundary condition? In the previous slide, actually, displacement is as a function of the x. So that in this stages, we have some those kind of relationship. X, u is a function of the x. Linear, with the linear algebra equation. This a and b is first time is an unknown variable. To determine what we applied in here, maybe we apply the position x1 equal to u1, position x2 displacement is equal to u2. Those kind of boundary condition, we obtain maybe this displacement can be expressed some form of the u1 and u2 in here, but this part of some function of xx blah 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 blah. So here actually all displacement follow this linear relationship. However, let's remember, let's back into the beam theory. In the beam theory, maybe some although in the beam theory we handle the displacement in the vertical direction, maybe v, maybe function of x. At that time, the result, can you remember that? Maybe also the quadrature form, maybe. So that to solve those kind of equation, we spend our time to apply the proper boundary condition and to match the exact bending momentum equilibriums. So anyway, so although linear algebra system, linear elastic solid structure, displacement in the axis direction always can be expressed the function of the linear equation by x. But our assumption is in the finite element method, we also use the same linear assumption. So although so we have some equations, so that u1 and u2. Just think about when you put some the x1, I want to obtain the u1 value in here. So that in here, this n1, what is, I assume that some function of the x, and then when you adding x1, at the time this become 1. However, when I put some another value x2, this part become 0. Similarly, I'm going to put some function of the x and 2. When I put some the x1, this become 0. When I put some the x2, this become 1. Yeah, when I have those kind of function, when I put some the x1, this become u1. At x equal to x2, this become to u2. Yeah, we can obtain. Yeah, let's back into the previous slide. Maybe in here. Yeah, here. When you put some the x equal to x1, x1, this part remains. However, this part become 0, so that u2 can be cancelled out. When you put some the x equal to x2, this part become 0, so that at that time u1 can be cancelled out. This part has those kind of some characteristics or relationship as function of the x, so using those kind of characteristics, we put some of those kind of function. We call it the shape functions or displacement functions for the linear algebra, so finite element method system. So just to remember that these functions, maybe we call it the shape function, but maybe we are going to handle the more details in the next slide.